Hello everyone, my name is Ariana Mondiri and I'm from Creighton University. So my presentation today is about applications of TDA to small molecules. So to start with the motivation, when we think of TDA, the main advantage that we get is that we're able to capture the global shape of things. And when we think of small molecules, this is different from more traditional molecular descriptors or focused on capturing local features. So during this experiment, we had some questions in mind that include, can topology distinguish molecular classes? Do ring systems create persistent features? How sensitive is TDA to bond ordering? And can we capture essential structures? So we're basically going to show that TDA is useful for molecular classification. And so for that, we will mention two datasets, the mu tag and the PTCMM. So when applying TDA to small molecules, what we really care about and what's really important is that the small molecules have a rich topology with aromatic rings, and they have a physical complexity that we can capture using full quantum mechanical or force field models. But here we want to extract geometric summaries, which in this case are less computationally intensive. So we use two different matrices for the distance. We have an unweighted distance where we treat everyone equally. That way we are able to capture the pure connectivity topology. And this is opposed to a weighted distance where we try to reflect the chemical strengths of other molecules. We also make use of the extended persistence as opposed to the ordinary persistence. That way we have a fuller fingerprint of the shapes of the molecules. So here's a practical workflow for information. At the end of the slides, there's a link where you can access the code and your implementation. So everything is done using Python and the Ripso library. So we start by constructed and unweighted Rips filtration, and then we compute ordinary persistence. We form complementary filtration, and then we compute extended persistence, and then we visualize and compare. So here we really want to develop an intuition about how things work and what TDA captures, and if there's like a really distinction between our small molecules. So if you look at the first visualization on the mu tag, we can compare it to the molecule 195, and we can see that they both have a different structure. And this difference is really captured by the persistent diagram using extended persistence for the homology group 1. So if you look at the mu tag, here we have 8 features. And if you look at the molecule 195, you have an extra feature. If you look at the range 2, there's a difference that we can notice for the birth for the molecule 195. It starts at 1 and it ends at 6. For the mu tag, it starts at 1 and ends at 5. That basically just tells us that a filtration captures things at a bigger scale for the molecule 195. And for the death, the range is the same. Its absolute value is 1, but for the molecule 195, it's from 6 to 7. And for the mu tag, from 5 to 6. And other than that, all the other diagrams are similar outside of the diagram for the homology group 2 using the extended persistence. The molecule 195 has an extra feature here, but it just basically tells us that we're able to capture some differences across molecules, and this gives potential to some classification tasks. So we can have different classification schemes. The one other richness, which is the one we're going to use, basically it's being able to separate aromatic rich pharmacophore from simple alkane scaffolds, which are believed to be less expressive. You could also do functional group class, biotoxicological role or size and branching. And so our expectation here is that molecules rich in aromatic or multiple bonds will show much tighter connectivity, and their represent diagrams, and single bonded tree-like molecules will merge more slowly and exhibit no genuine loops or cavities. So to demonstrate that, we use the PTCMM dataset, which is composed of 20 molecules. So we can make two groups. We have one group that is composed of high unsaturation molecules. Those are molecules that have many aromatic double or triple bonds. So we have 10 of those. And on the other group, we have low unsaturation molecules. So those are molecules that are dominated by a single bond and have kind of a tree-like structure. So we also have 10 of those. So if we start with a visualization, we can take two molecules from the high unsaturation group. We have the molecule 127 and 301. And as you can see, they have a complex structure, especially when you look at the molecule 127. And this is kind of reflected in the person diagrams here, where I pick up features from the homology group 0, homology group 1, and homology group 2. Similarly, for the molecule 301, these features are captured from the homology group 0, 0, 1, and 2. Now looking at two other molecules from our low unsaturation group, we have the molecule 152 and 195, and you can see they have a much more simpler structure. They have a single bond and a tree-like structure, and they have similar Bayesian diagrams here. The big three features get captured from the homology group 0, 1, and 2. And here we can kind of make use of our intuition. And if we do, we somewhat have mixed feelings, because if we consider the molecule 127, when you look at it, there's like a complex structure with many cycles. And this is reflected in the persistent diagram. And when you look and you compare at the two low unsaturation molecules, you can be satisfied with what you see, because here you have a complex structure, richer the person diagrams as opposed to those. So this kind of follow our intuition. But then where you can have mixed feelings is that, okay, so this is also a complex molecule. There's more than one cycles, many cycles. And when you compare it to the simpler molecule with a single bond, the diagrams are the same here when you look at the molecule 301 and the molecule 152 and 195. So here you can have mixed feelings if you just consider your intuition. But if you go further in our analysis and we consider the bottleneck distances, we can see a pattern that's interesting. So first, if we compare the bottleneck distances of the molecule 127 and the other three molecules. So as a reminder, the molecule 127 is the one that exhibited the most differences in the person diagrams. So we can start by looking at the molecule 127 and compare it to the two simpler molecules, one with a single cycle. So we can compare it to the molecule 152 and 195. And our expectation is that the bottleneck distance should be higher because they have a significant difference. So if you look at the molecule 127 and you look at the graph, the molecule 152 and 195, you have a bottleneck distance of 1. And when you consider the bottleneck distance, you need to look at it in relation to the other distances are displayed. So here 1 is our highest value and 0 is our lowest. So we can say that that 1 here is pretty high. So this is kind of to be expected. And when we compare molecule 127 to the molecule 301, we can kind of expect also a higher bottleneck distance, because even if when you look at it, they both have a complex structure. If you look at the diagrams, you can obviously see that there's like a difference. Here you have 5 features, and if you have 3, here you have 3. And looking at the bottleneck distance, 127, 301, the bottleneck distance is also 1. Now comparing the two low unsaturation molecules, we have the 152 and 195. Those have a structure that is pretty similar when you look at it, one cycle and then a tree-like structure, and then they have the same person diagrams, and so you would expect the bottleneck distance to be pretty small. So if you look at it, we have the molecule 152 here, 195, and the bottleneck distance is 0, which is kind of consistent with what we would expect. And now looking at the molecule 301, and we're going to compare it to the two molecules from the low unsaturation group. And here you can kind of have mixed feelings because this one is from the high unsaturation group. And when you look at it, there's some complexity that you can obviously see compared to these two simpler molecules. But when you look at the diagrams from the molecule 301 and the two low unsaturation molecules, the diagrams appear similar. So looking at the bottleneck distance, that's the molecule 301, and the two simpler molecules from the low unsaturation group, the bottleneck distance is 0.5. So there's actually a difference that we can see. And here my guess is that even though the person diagrams look the same, there might be points that are stacked on top of each other, or something like uh, point that are on top of each other that is like that got picked up when considering the bottleneck distance. So, and also when you look at the unweighted distance and the weighted distances, the values are different, but the pattern is the same. So in that case, there's no difference between whether we have an unweighted or a weighted distance. So that is it. And if we do more, we do more analysis and we perform a permutation test, we're first doing using 6 pairs. So here we have a first pair, a second pair, third, 4, 5, 6, and then we do a permutation test. We first see that there is no statistical difference. But if we consider all the molecules, so we have 20 of those, so that makes 190 pairs. If we consider all the molecules and we run the permutation test again, then yes, you can see that there is a statistical difference. And so if we summarize what we did, we analyzed the PTC data sets, then we built our distance matrices, and then we computed the person diagrams and then the extended persistence. And the key finding when we look at the visualization and the comparison groups and the permutation test is that the bottleneck distances differ between the small molecules, and that shows that TDA is sensitive to our chosen molecular classification. And so here the future directions are, obviously we can consider the other classifications schemes that we mentioned, the functional group class, the biotoxicological role, and the size and branching. And we can also perform deeper analysis, because one drawback of TDA is that interpretation is limited and it's really hard to link what we see back to molecular substructures and real world properties. And we can also do more analysis to try to understand why we see what we see. So here are the links that I mentioned. Thank you for your attention.